on lab day, a lot of you missed some things that we were doing to find net forces. So what we had talked about is, what if somebody pulls on somebody this way with 20 newtons of force, and somebody pulls the other way with 20 newtons of force, what would be the net force? And he said that was 0 because they cancel out. Or what if they both pulled the same direction, 20 newtons, what would be the net force? We found that would be 40 newtons, and the person accelerated much faster. Well, then the next question is, so 20 plus 20 in the same direction is 40, 20 plus 20 in the opposite directions is 0. Well, what is 20 plus 20 at a 90-degree angle? So for that, we went down to the commons, and we have a hovercraft that we had somebody ride on that was floating on air, and we did this very experiment. So what happened is we had one person pulling straight north with 20, and one person pulling straight west with 20. And we found the hovercraft moved in this direction. Well, what we did next is we tried to figure out, well, how do you have a direction of the net force in this direction? How do you know the magnitude of it? Because every vector has a magnitude and a direction. Well, we figured out if you pull exactly opposite of that, that would be the force that would balance these two. It's called an equilibrium force. So if this is the force A and this is the force B, or if A plus B equals this amount, it's exactly balanced by something going the other direction. You can call that a C scale if you want to. And experimentally, we found that to be 28 newtons, exactly opposite of that. So from that, we surmised that the net force acting at 20 newtons straight north plus a 20 newtons straight west was actually 28 newtons in the northwest direction. Now, then we came back into the classroom and we did the same thing, but we did it graphically. So to do this graphically, we had to set up a scale. And the scale that would fit in this picture would probably be 1 centimeter equals 2 newtons. So if 1 centimeter equals 2 newtons, and my forces are in fact 20 newtons, that would mean we would need a distance of 10 centimeters. So it's pretty easy math. So what that means is to draw the north vector. Remember, if vectors need both magnitude and direction. So I have to draw one that's 10 centimeters long, and make it a vector, you have to have a direction. So from there to there, it's 10 centimeters, and that's going to represent my 20 newtons straight north. Then, if you wanted to just get this spot on, you would take a protractor and place the 0 hole on the 0 there, line up your 90, find out where your 0 is over here. We want to be exact to make sure you have exactly a perpendicular line, but also being 20 newtons, it's also going to be 10 centimeters long. And at the very end, put your little arrow at the end. So from there to there, 10 centimeters. Now this is the parallelogram method for adding vectors together. It makes it easier to see exactly where things move. So if I want to make this exactly parallel, I'm going to make sure my line, again, is at 90 degrees. And I'm going to make a line going this way the same length, 20, because it's going to be very similar to this vector right over here. And that means I'm going to draw that up to there. And I'm not putting an arrow on it because I'm not going to call that a vector, and here's why. I'm just trying to make a parallelogram so I know what to draw. It's called my resultant vector. So now I have a parallelogram. Sure, in this case it's a square because both sides are the same. This is 20 newtons north, this is 20 newtons to the west. Well, now to find my resultant, you can see if this is the hovercraft, it's going to clearly go right in between those two. So to find out what the net force is, all I have to do is, one, measure that length, but I need to draw the line in between there. So I'm going from the 10 clear down to here. Okay, so that is 24.2. From sorry, not 24, it's actually 14.2. So the length of this line is 14.2 centimeters. Now, being a vector, you have to have the arrow at the end there. Now remember, the scale is 2 to 1. So if it's a 14.2 centimeters, what would that be in terms of the magnitude for the force? Well, all you do is times 2. So times 2, this is a 28.4 newtons, which, if you remember, is very close to the amount that we found experimentally we pulled backwards. It was, so for the final answer, I can't just have magnitude, I also have to have direction. Well, if I measure this angle, you're going to find it's just a bisector, that this is actually just 45 degrees. And if it's exactly 45 degrees, I can call that northwest, because that's exactly what northwest means. So if you're allowed today, what you guys are doing is the same kind of thing, not with the uppercut, because nothing moves. But what you have is a round table. And on this round table, you'll have a scale A, a scale B, and the equilibrium or balancing force when we plane backwards is the C. And what the C should represent is the addition of what A plus B is in this direction.